so how can you tell when you have an integral for which you're going to try integration by parts? Usually a product where it's not a UDU integral. You always look for that first, right? Is it a known integral or is it a UDU integral? And if you've got a product, usually a polynomial term multiplied with a transcendental function. One of your trig functions, your inverse trig functions, logarithms, or exponentials. That's usually a giveaway that you've got an integration by parts. And remember, always look for a basic integral or a UDU first. And then some of the integration by parts don't even look like they'd be integration by parts. A logarithm by itself, an inverse trig function by itself, those would all involve integration by parts. And I showed you, I think, secant cube. It was an integration by parts. Maybe I showed you that. Those of y'all coming in, do you have any homework questions you want me to work before I get to blowing and going? Because there's some on that homework that are a little bit different. Okay, well, let's go back and finish up 7.2. Remember doing integration by parts, where we have some sort of x to a power times the sine of x to a power times the cosine of x, anything involving a logarithm, x to a power times e to the x, any inverse trig, and any combinations of e to the x, sine of x, or cosine of x. These are the two that become circular. We'll look at some of those today. And our integration by parts formula was that if you're integrating a product, one of the terms has a derivative you know, the other term has an antiderivative you know. Then you can expand that out as uv minus the integral of v du, where this v is the antiderivative of the term here, and du is the derivative of the term here. So one example, an integration by parts, is something like, I don't know, let's go with x cubed times the cosine of 2x. Badly. In here. So that looks like the second one here. And I can integrate either one of these pieces, but the bigger one, the bigger part or the main part, would be the cosine. So I'm going to call all of this back here the dv, and that's going to be the u. I'm going to stop that and keep going. Good. That was news about my granddog. Okay, so we need to calculate the derivative of u. And the derivative of x cubed will give me a 3x squared. Oh, stop that.
So your granddog sent you music?
These are my texts. I took care of this dog when my son first took his job. He took a job down in Brownsville, and he couldn't bring his dog with him because he had no place to live. So I took care of this dog, and he became my dog for like 6 months. And then I had to bring him back about a month ago and give him back to his boy. As soon as he got there, he got really sick. He couldn't keep food down. He was just having trouble with his digestion. And he couldn't get a vet there. He'd have to drive an hour away to get a vet. So if things weren't going to shape up, I was going to get the dog back and take him to my vet here, who's really good. But he just got a vet appointment, and he said, this vet's doing really good, and the dog's doing really good, and life is good again. It's amazing how much I worry about a dog. All right, you guys got to have pets? I'm a cat person. Boy, cats were pissed off when I took that dog in. They were looking at me like, I'm going to leave you a surprise somewhere, girl. Okay, so I'm going to integrate this. What happens when you integrate a cosine? What do you get? You get a positive sign. What's this 2 going to do? It's going to give us a 1/2. So my v is going to be a 1/2 sine of 2x. And so now let's put it in the expansion. So I'll take my u and multiply it with the v. So I'll have x cubed times 1/2 sine of 2x. So let me write that as x cubed over 2 sine of 2x minus the integral of v times du, which is a 3x squared dx. Typically, I like to write the polynomial term in front. So let's write this as 3/2 x squared sine of 2x dx. Take it up here. That's a very similar integral in structure as the one we started with, a polynomial term times a trig function. So we've got to do integration by parts a second time. Let's keep with the same plan. Let's keep choosing the polynomial term to be the u and the trig term to be the dv. U to be 3/2 x squared, and dv to be the rest of the integral. So we need the derivative over here. The 2x will cancel the 2 and just leave me a 3x dx. Integrate over here, we'll get a negative cosine and yet another factor of 1/2. So v is going to be minus 1/2 cosine of 2x. So let's bring it down here. This is still part of the antiderivative, so let's not lose it. X squared over 2 sine of 2x.
Can you change it from x cubed to x squared?
You're absolutely right. Thank you. Okay, x cubed over 2 sine of 2x minus, now we're going to put the integration by parts scheme in here. So I want to make sure I don't lose my minus sign. So let's put brackets. And then we're going to put our uv minus the integral of v du. So my uv, let me go ahead and simplify a little bit. I'm going to have a negative 3/4 x squared cosine of 2x. minus the integral, again, I'm going to try to simplify here, v times du. Now my v is negative, and I'm going to put that negative with this negative. And then I'll have 3/2 x cosine of 2x dx. You okay to there? And I want to simplify as much as I can. So in this step, before I try that integral, I'm going to distribute this minus sign through the brackets and get rid of these two brackets. That'll give me x cubed over 2 sine of 2x. These two minuses will give me a plus 3/4 x squared cosine of 2x. And now this gives me a minus 3/2 x cosine of 2x. So what do you think about that last integral down there? Three halves x cosine of 2x. How do you want to do that one? It is another integration by parts because of the x in front. Anytime x in front of a trig function. So I've got third integration by parts. Really no place to put it. So I'm going to erase some of this stuff over here. Put it up here. Yes.
Does the power on the x beginning tell you how many times you have to do the integration per
It
part?
really does. In most cases, it does. There's one on your web work that's going to kind of trick you. But yes, the power in there tells us. I got a power of 3, and I've got 3 integration by parts going on here. We're going to keep the same format. U is going to be the polynomial term, and dv is going to be the trig function. I think I could put that about right here. Use the polynomial, 3/2 x, and dv is the trig function. dv up here. We take the derivative here, and we'll just get a constant this time. The antiderivative here is going to give me a positive sign with a 1/2. So now I've got to go back over here. Let's write down the first two parts of our antiderivative again. That's the x cubed sine of 2x, x cubed over 2, sine of 2x, plus 3/4 x squared cosine of 2x. Minus, now the minus is going to have to be in front of brackets because in here is where we put our integration by part. Excuse me. So in that box, I'm going to put, using these u's, VU's and such, I'm going to put my u, v minus the integral of v, du. So u times v will be 3/2 x times the 1/2 sine of 2x. So let's write that as 3/4 x sine of 2x. Minus the integral of v times du. So I'm going to take my 1/2 sine of 2x, multiply it with 3/2 dx, and get 3/4 sine of 2x dx. Now, before we do the integration, let's get rid of the brackets. I'm going to distribute this minus sign, take the brackets away, make that a plus. But I'm running out of room to write, so I'm going to do that right here. Take the brackets away, make that a plus. And now I can integrate that because now that's just a constant times a trig function. I can just integrate the sine of 2x and get a negative 1/2 cosine of 2x, and then we're done. What I said, I'm going to get a negative 1/2, so that's going to become a 3/8 cosine of 2x. And we're done, so we tack on the big old plus c. So it's really amazing to me that the derivative of that big line right there is just going to give us this. Isn't that amazing to you?
Amazing.
Amazing. And if I was just some bored college student, I'd probably take the derivative of that to make sure it did. But life's too short. Okay, so what I was telling you last time was that all of this work that we did here with 3 integration by parts, if we know in advance it's going to be repeated integration by parts, we can do in table form. So an x to a power times a cosine, x to a power times a sine, x to a power times an e. Those are the ones that can be done in table form. And let me show you how to do all of this work in one table. So I don't need any of that junk, I just need this. So let me erase everything. So this term here tells me that I'm going to have a repeated number of integration by parts. But that's only true because this is an x to the first power, right? If this were x to a 4th power here, I would just do an ordinary Udu substitution. So we're going to do this in table form. What you need to have is a term whose eventual derivative will be 0. So once I take a few derivatives of x cubed, one of my derivatives will turn into 0. If this had a fractional exponent or a negative power, this won't work. Okay, so we'll make a column for u. We're going to make a column for dv. And we're going to pick u to be the polynomial. We're going to take as many derivatives of that as we can until we get 0. So here's the 3x squared. Here's 6x. Next one 6. And then finally I get 0. Then let's put the trig function over here. And for every line that I have in my table, I've got to take an antiderivative. The integral of cosine and give us a sine. The 2x is always going to spit out a factor of 1/2 when I integrate. So the next integral is going to be a negative cosine. When I put another 1/2 out here, it gives me a 1/4. The next integral is going to be a sine. Put out another 1/2 gives me a 1/8. That's negative. And now one more antiderivative. Integral, a sine is a negative cosine, so that's going to be a positive constant. The constant will be multiplied by 1/2. So I get a 1/16 cosine of 2x. Okay, now look at my table and look at the antiderivative. The first term has to be an x cubed over 2 sine of 2x. Can you see where I'm going to get that out of the table? Here's my x cubed over 2 times the sine of 2x. Then the next term is a positive 3/4 x squared cosine of 2x. I have a negative. We need a positive. In this table form, you alternate signs down the diagonal. So the first one's going to be plus. The next diagonal here is going to be minus, so you change the sign here. So that'll give us plus 3x squared over 4 cosine of 2x. Now my next diagonal, keep the sign. So I'll have a 6 over the 8 with the minus. 6 over 8 is 3/4 with the minus, then the x, and sine of 2x. And then my last diagonal here, back to minus, so we change the sign on that one. A negative 6 over 16 simplifies to a negative 3/8. Shabam, there's our negative 3/8. And then the cosine of 2x. And now we're done. Isn't that kind of sweet? Yes, sir.
Do you always start the table with a positive number?
Yes, sir. Keep the sign, change the sign. Keep the sign, change the sign. Always in that order.
So if it happened to be negative right off the bat, you keep it
Keep
negative?
it, got it. Read that as keep, change, keep, change. Okay? So let me give you one. Polynomial term and e to a first degree power will be repeated integration by parts. Take a wild guess how many times. Don't want to do that one step at a time. Let's all do it in a table. There should be 5 integration by parts steps, so let's do it in the table form. Choose the polynomial to be the u. You've got to have something whose derivative vanishes. Make you a long table. Yours will be a little bit longer because it takes a while for all your derivatives to go to 0. X to the 5th, e to the negative 2x. What do you get when you integrate e to the negative 2x? What's this 2 going to give you? You're going to get a negative 1/2 with each integration, right? You get itself times negative 1/2 each time you integrate e to a power. 5x to the 4th as your second line. 20x cubed. 60x squared. 120x. 2 more rows. The next one's 120. And then you're going to need the last row to have the 0 in it. So each time I have a row, I've got to integrate e to the negative 2x. And so you get itself times a negative 1/2. So the next one, we'll find negative 1/2 times another negative 1/2, and it gives us a 1/4 here. Integrate again. Get another factor of negative 1/2, so I have a negative 1/8 there. E to the negative 2x. Now I get a positive 1/16. Another integral. And I get a negative 1/32. We need one more here. Negative 1/2 gives me a positive 1/64. You okay to there? Now we're going to go diagonally. Keep, change, keep, change, keep, change. So I keep the sign here. That'll be x to the 5th over a negative 2 e to the negative 2x. Oops, don't want it red. Let's go black. So what did I say? A negative x to the 5th over 2 e to the negative 2x. Next one's a plus, or change, change. So I'm going to have a minus 5/4 to the 4th e to the negative 2x. The next one's a keep. Keep 20/8. I'm not even going to reduce. So a negative because of the 1/8. Excuse me, x cubed e to the negative 2x. This one we change, so it becomes a negative 60/16. X squared e to the negative 2x. This one we keep the sign, but I've got a minus from there, so it's a minus 120/32. And I have an x e to the negative 2x. And then finally change the sign to give us a negative 120/64 e to the negative 2x. And we're done, so we tack on the plus c. Smart person would have factored out the e to the negative 2x way at the beginning. You like? No? There's no pleasing some people. Okay, now let's do an integration by parts that becomes circular. And that happens when you have an e to a power times a sine or a cosine, usually. So let's see, we just did a cosine integral, let's do a sine integral. Go with another e. Let's put a 3x here. And let's put a 4x here. You'll see that this is an integration by parts. which becomes circular. We're going to end up in one of our subsequent steps with the same integral that I'm starting with. But you've got a product, and neither one of these terms has a derivative that's eventually zero. So the table is not an option. We can integrate either one of them. So pick your favorite to be the dv, and the other one's the u. It doesn't matter. I'll just go with the u as the e to the 3x, and the dv is the sine of 4x. And then we need a du term. We'll get the 3 from the derivative of the power. And then we get the e to the 3x back. And we integrate here. Integral of a sine is minus a cosine. And we've seen that a number here gives us the reciprocal out front there. I'm going to put the scheme up here. We've got UV minus the integral of v times du. Take some room over here. Okay, so u times v is going to be a negative 1/4 e to the 3x cosine of 4x. Minus the integral of v times du. And so let's kind of keep it in the order of our problem. If I multiply these two together, I'm going to get a negative 3/4 e to the 3x cosine of 4x. Negative 3/4 e to the 3x cosine of 4x. I'm going to keep the 3/4 inside the integral, but I'm going to put the two minus signs together. You know how easy it is to lose a minus sign. So let's go ahead and move this one out and make that a plus sign. I'll just do that with my eraser, like that. But then you see we've got an exponential function times a trig function, so we've got to do integration by parts again. It's very important that you keep the same choices. Otherwise, not only do you go in a circle, you go backwards. So I'm going to keep choosing the exponential part to be the u and the trig part to be the dv. So this time u is going to have the 3/4 e to the 3x. And the dv is the cosine of 4x. The derivative here is going to give me another factor of 1/3, which would cancel that 3 on top. So du is just going to be 1/4 e to the 3x. And here I'm going to get another 1/4 when I integrate. Yes, sir.
When you took the derivative of e to the 3x.
Oh, it's going to be a 3, so this is going to be a 9. Thank you. That's why you looked at me funny. That's what you're there for. See how easy it is to make a mistake on these, though. You've got to really concentrate when you're doing these. Yes?
Like the cosine for it, or not the cosine.
It does. See? Where else did I mess up? 2 mistakes in one line. That's not bad. Okay, so I'm going to put the integration by parts right there. Let's pull this problem down. Let's bring the equal sign here. Copy that term. Now I got a plus, so I really don't need brackets if I've got a positive sign here. So let's just do my uv minus the integral v du. So uv is going to be 3 over 16 e to the 3x sine of 4x. Minus the integral of v times du. So I'm going to get 9 over 16 e to the 3x sine of 4x. So here's where I notice, my gosh, this is what I had at the beginning. So in order to integrate e to the 3x sine of 4x, I need to integrate e to the 3x sine of 4x. So I'm not going to do any more integration by parts. I'm going to remember that I've got this over here, and we're going to make an algebra problem out of it. I'm going to take these from over here. You can think of the 9 over 16 as being a multiplier of the integral. And I'm going to combine them with this one. So I've got the integral over here and negative 9 over 16 of that integral. I want to add them together, right? Since it's subtracted here, I'm going to add it to the other side. Let's just call that integral I. And here I have one of those integrals. So I'm putting that over here. And you're going to add for me, excuse me, one of those integrals plus 9 over 16 of those integrals. Get you a common denominator. Add them. What do you get? 25 of those integrals. So we have 25 over 16 of those integrals is equal to the last two terms, negative 1/4 e to the 3x cosine of 4x plus 3 over 16 e to the 3x sine of 4x. So the last step is to solve for our integral by dividing by this number. If you divide by a fraction, you can flip and multiply. So I'm going to multiply both sides by 16 over 25. And that should be our answer. You can simplify it, I suppose, if you distribute that through there. Got enough room to write it up here. And so, that one stuff. Yeah, we're going to put that over there and put the plus C on it. All right. Doggy's going to live. So let's distribute the 16 over 25 through there. 16 over 25 times a negative 1/4 is a negative 4 over 25. E to the 3x cosine of 4x. 16 over 25 times 3 over 16 gives me 3 over 25. E to the 3x sine of 4x. And now we're done, so I'll put the plus C on right here. Okay?
So when you have the 1i plus 9/16 I, does the fact that it's minus in the original equation matter at all? So it's like,
Not necessarily, because if some of these are negative, this might be a plus. But whatever it is, you do the opposite to get them together, right? So if I want to get rid of a minus here, I add it here. I have a plus here, I subtract it here. So it doesn't matter what the sign is. It's just going to affect the coefficient over the end. So be careful, be alert when these things happen to you. Either the something times a sine or a cosine. You'll see this also happens when you integrate a secant cubed or a cosecant cubed, or any odd power on secant and cosecant. Eventually becomes circular. Okay? All right, let's move away from integration by parts and get into section 7.3. 7.3 is one of your longer sections in this text. We've got to look at how to compute integrals that involve trig functions. And then we're going to look at integrals that involve usually radical signs, and we need some way to get rid of the radical sign. So the first part we're going to look at is the bunch of trig integrals. So we're in section 7.3. There are two parts. We're going to do some trig integrals. That'll be part one. And then we're going to do some integrals by trig substitution. Those are really fun. And those are part two of this section. Oops, go to Roman numerals, stick with the Roman numerals. When we're doing trig integrals, we're going to look at integrals that involve products of sines and cosines, integrals that involve products of tangents and secants, and integrals that involve products of cosecants and cotangents, or any one of those by themselves. Integrals with sines to a power, cosines to a power, tangents to a power, and so on. And we're going to try to develop some strategies so that we don't flounder and panic and things like that. So our first type of trig integrals that we're going to look at is looking at integrals of the form sine to a power, let's put that power as an m, times cosine to a power, let's put that power as an n, but before we develop our strategies, let's think all of the ways sines and cosines are related. Firstly, we know that one is the derivative of the other, give or take a minus sign. If you take u to be a sine, then du will be a cosine. If you take u to be a cosine, then du is a sine. And like I said, always see if you can manipulate an integral to be a u du integral. If I pick u to be a cosine, everything else in the integral has to be a sine, and vice versa. So I need some trig substitutions. And the one that comes to mind is that sine squared plus cosine squared is 1. So what I just said is, if u is a sine of x, then du is equal to a cosine of x. If u is a cosine of x, then du is minus sine of x dx. If we're going to choose u to be a sine, du is a cosine, that means the rest of the integral has to be in terms of sine. So we'll substitute out our cosines using the identity that cosine squared of x is 1 minus sine squared of x. If I do this case, and my du is a sine, then everything else in the integral has to be a cosine. So we'll manipulate the Pythagorean identity to get rid of a sine squared as a 1 minus cosine squared. But in order for this to happen, we're going to need, after you pull out one of these factors, we're going to need the other trig function to have an even power. Right? We're going to need the even power. So if I'm going to employ this strategy, I'm going to need either this power or that power or both of them to be an odd number. So the first approach is, I'm going to use that if M or N or both are odd. Then I pull out, good gosh, one factor of the odd one. Why are you stopping? I'm in class. Pull out one factor of the odd trig function. That goes with, when I pull it out, that goes, this will be the du. And then write the rest of the integral in terms of the other trig function. Okay, this will be a basic UDU integral that remains. So for instance, suppose I want to integrate a sine cubed multiplied with a cosine squared. The sine has the odd power. Take one factor from that and slap it next to the dx. So if I'm going to pull one of those out, that's going to leave me a sine squared here. The one that I want to pull out goes over here. So I'm setting that up as the du term, which means everything over here has to be cosines. So next I substitute this out. Sine squared is 1 minus cosine squared. So I got it the way I want it. Sine of x dx is going to be my du. The u is just going to be a cosine. So I can change it from a trig integral to a polynomial integral. Take u to be cosine. Don't take any of the powers with it, just take u to be cosine. And du is a minus sine of x dx. So I'm going to replace this sine of x dx with a minus du. And we'll have 1 minus u squared times u squared times a minus du. Is that an integral you can do? Almost, right? What do I got to do next?
Could you distribute the u squared?
Yeah, we got to get rid of the product, so just multiply it out. I'm going to have a u squared minus u to the fourth. So let's just integrate and get a u cubed over 3 minus u to the fourth over 4. I'm sorry, u to the fifth over 5. And let's distribute the minus sign. And each u is the cosine of x. Works like a charm. UDU integral by getting an odd factor out. That means the remaining power on that trig function is even. Write that trig function in terms of the other trig function, so that will play the role of u, and then do a UDU. So in the next example, I'd like you to integrate sine to the 5th power of x. Compute the integral of sine to the 5th dx. Unfortunately, it's not as easy as saying that the integral of sine to the 5th is sine to the 6 over 6, right? Because we don't have a u to the 5th integral. If I have a u, then I need a du, and I don't have the derivative of the sine out here. So you can't just add 1 to the power divided by the new power. But we saw how nice it worked if I pulled out one factor of sine and then try to write the rest of the integral in terms of cosine. So give it a shot while I erase. So we got one factor of the sine. Setting that up to be the du term. So you got to get rid of this and write it in terms of cosine. Sine to the 4th is sine squared squared. And we're doing this. Sine squared now can be replaced with 1 minus cosine squared. I'll give you a few minutes to try it on your own. See if you can get some success out of that. Okay, so I'm going to take out the sine squared of x and put in a 1 minus cosine squared. So we'll have a 1 minus cosine squared squared. Eventually, you're going to have to multiply it out. You can multiply it out now, or you can multiply it out after you put the u in there. I'm going to go ahead and put the u in there. Take u as the cosine of x. So the du is minus the sine of x. So we have a minus out here, 1 minus u squared squared du. So we do have to square it. Let's go ahead and square it right now. I'll get a 1 minus 2u squared plus u to the 4th du. Now let's integrate with our power rule. U minus 2/3 u cubed plus u to the 5th times the 5th plus c. We'll substitute the cosine of x in for each u, and I'll distribute the minus sign. We'll get minus the cosine of x plus 2/3 of the cosine cubed of x minus 1/5 of the cosine to the 5th of x plus c. Is that what you did? If they're both odd, you have your choice. Just pick a factor from the odd one or an odd one, write the rest in the other trig function, and so on. And you know from all of our trig identities, there's an infinite number of ways you can rewrite your answer. So if you're like Googling your answer on the web, it might give you something that looks really odd, really funky compared to what we've been doing in class. So I'd rather you just look at the way we're doing this. So if you see an odd power anywhere on a sine or cosine, this should work for you. Now, if they're even, we've got to try something totally different. Because if you've got even powers and you pull the term out to be the du, then you've got an odd power trig function and you can't rewrite it using the Pythagorean identity. For example, if I have a cosine to the 4th and sine to an even power, and I pull out a cosine, I've got a cosine cubed left. I don't have a substitution for a cosine cube, only even powers of cosine. So we try something else. And we're going to use the same identities that we used when we were integrating sine squared and cosine squared back in chapter 6. Those are going to be called power reduction formulas. So in the case if both m and n are even, those are the powers on the sine and cosine. Use the fact that the cosine squared of x is 1 plus the cosine of 2x all over 2, and the sine squared of x is 1 minus the cosine of 2x over 2. These aren't integral formulas. Those are the trig identities that we're going to call the power reduction formula. So if you've got an even power, you factor the even power as a cosine squared to whatever to give you that even power, sine squared to whatever to give you that even power. Then you put these in there and you'll have to multiply them out, and then hopefully you end up with an integral that you can do or use power reduction again. So it involves a lot of algebra. This is messy algebra to do the even power ones. But we got this algebra thing down, don't we? Especially if you watch me and keep me from making mistakes. All right, so let's integrate just the product of cosine squared with sine squared. So again, let me reiterate. I can't use the same strategy as before. If I pull out a sine of x, that leaves me a sine to the first power. And I don't have a substitution for a sine to the first power. So that's not an option, what we did earlier. Now we're going to go and do this. I'm going to replace cosine squared with this, sine squared with that, multiply it out, cross my fingers, and hope I can do the integral. So I replace cosine squared. Now replace sine squared. And let's simplify. Take the half times a half and pull it out front as a 4. And now I'm going to multiply 1 plus the cosine times 1 minus the cosine. What will I get when I multiply 1 plus cosine with 1 minus the cosine? We're going to get 1 minus the cosine squared of that 2x. So multiplying it out gives me 1 minus the cosine squared of 2x. And I know how to integrate both of these. In fact, I can even make it shorter because I know what 1 minus cosine squared is equal to. What's 1 minus cosine squared? What's my trig identity? That's sine squared. So I can replace this with sine squared, or I can integrate it as it is. I'm going to go ahead and replace it with sine squared. And I remember my integral for the sine squared of theta was theta over 2 minus the sine of 2 theta over 4. So I've got to do a Udu substitution to take care of the 2x. Let's let u be 2x. Du is 2 times dx. So 1/2 du is dx. And so we're integrating 1/8 of the integral of the sine squared of u du. So in terms of the variable u, we should get u over 2 minus the sine of 2u over 4 times that 1/8. But each u is 2x. Put the 2x in there. We're essentially done. We can simplify if you want, but I don't want. So we're done. Okay? All right, so let's see. How about we integrate cosine to the 4th of x? Again, it's not as easy as adding 1 to the power and dividing by the new power, because I don't have a UDU integral. Got a big old even power on that cosine. So I'm going to think of cosine to the 4th as cosine squared squared. And where I have the cosine squared, I'm going to put this in. So cosine squared in the parentheses is 1 plus the cosine of 2x over 2. That's this term. Now I got to square that and hope that I can integrate what's left. All right, so I'm going to do my part. If I take that 2 on the bottom and square it, I get 4 on the bottom. So I'm going to put a 1/4 out front. And now it's your turn. 1 plus cosine 2x all squared. Square it as you would a binomial and tell me what you get.
One plus 2 cosine 2x plus cosine squared 2x.
Good. So I got a sum of 3 integrals that I know how to do. Again, we got to do the Udu substitution because of the 2x. So I'm going to get a 1/8 out here. And then I'm going to integrate 1 plus 2 cosine of u plus cosine squared of u du. Now we can integrate. I'm integrating with respect to u, so this is where I get a u right here. Integral of cosine of u is a positive sine of u. So I get 2 sine u here in the middle. And now from chapter 6, the integral of cosine squared of u is u over 2 plus the sine of 2u over 4. Last step is to put the 2x back in for each u. So I'm going to have 1/8 2x plus 2 sine of 2x plus 2x over 2 plus the sine of 4x over 4 plus c. Anything simplifying from there is fun for you. I quit. Okay? So you've got an odd strategy and an even strategy for sines and cosines. So as an extra challenge to you, what I want you to do this weekend, I mean, you got tomorrow to screw around and do nothing, right? Integrate sine to the first, second, third, fourth, and fifth. Integrate cosine to the first, second, third, fourth, and fifth. And you already know the 1 and the 2, so you're really only going a little bit higher. You do the same for tangents and secants. So let's look at the tangent and secant cases. If you're looking at combinations of integrals involving tangents and secants, you've got to remember which ones you already know how to integrate. Do you know how to integrate tangent to the first power? We did it in class. We wrote tangent as sine over cosine and got minus the natural log of cosine. Do you know how to integrate secant to the first power? We did that one in class too. That's a logarithm. That's the natural log of secant of x plus the tangent of x. Can you integrate secant squared of x? What's the integral of secant squared? Not cotangent, the regular tangent. Tangent, right? Derivative tangent is secant squared. Can you integrate tangent squared? Is there a trig function whose derivative is tangent squared? But there's a trig identity that relates a tangent squared to a secant squared. And we know how to integrate a secant squared. So let me write down all the stuff that I've just told you. So our next case is we're looking at doing integrals of the form tangent to a power. So let's see, I think I put an M on the first one. And secant to a power, where these guys are multiplied together. Our first attempts at doing these is to try to make our integral look like a u du integral. So let's refresh our memory what the derivatives of each of these are. So if u is the tangent of x, then du will be a secant squared. If u is a secant of x, what's the derivative of a secant? Derivative of secant of x is? Secant x tangent x. So we're going to ask ourselves, can I pull out a secant squared and then write everything else in terms of tangent? Can I pull out a secant tangent and then write everything else in terms of secant squared? Well, I've got to know my Pythagorean identity for tangents and secants. I know that sine squared plus cosine squared is 1. And so if I want to convert this to tangents and secants, I'm going to divide everything by cosine squared. And so there's my identity. Tangent squared plus 1 is secant squared. Tangent squared plus 1 is secant squared. So if I'm pulling out a secant squared and I want to write everything else in terms of tangents, then I'm going to replace all of my even powers of secants with tangent squared plus 1. But not this secant squared, that stays there. That's the remaining secants. If I pull out a secant tangent, then I got to write everything else in terms of secants. So I'm going to use this form that tangent squared of x is equal to secant squared of x minus 1. But now I got to figure out, what do I need for this to work? If I'm pulling out a secant squared, I've got to have even powers of secants left behind. So the case would be if n is even, or if the power on secant is even, do this. It's not as easy to say that if the power of secant is odd to do this. It's not that easy right here. But essentially, that's what you're going to do. If the power on secant is odd, do this, but you're not always going to end up with a Udu interval. So this is the easy case. Even power on secant is easy. You'll get a Udu integral. Odd power on secant is not as easy. Sometimes you get a Udu, sometimes you don't. It's our time of day here. 10:45, we got till noon though, don't we? Are we gonna make it? Have you forgotten that this is your favorite class? Do I need to remind you of that? That in this class, time is meaningless. I could do this for infinity. Isn't that what's going through your head right now? Your rumpus is saying something differently. It's saying, stand up, I'm dying. But your mind is saying, man, this is great. I could just do this forever. If only there were food. Right? Doesn't that make things last longer? All right, so let's integrate. Which one's my first one? Well, this one you don't have to do anything. Tangent cubed times secant squared. That's easy. You could have done that one in Calculus 1. Because
Secant squared.
secant squared is the derivative of the tangent. That's a UDU integral looking right at you. Take u to be the tangent, du is secant squared. So you're just integrating u cubed du. Okay? That's the du term. Secant has an even power, pull out a secant squared and make that the du, which means the u has to be the tangent. Not the tangent cubed, just the tangent. So our integral is simply u cubed du. So we get 1/4 u to the 4th, where u is tangent of x. Now let's put some other power on the secant, but let's make it an even. Let's keep our tangent cubed, but let's make that maybe a secant to the 6th. Let's see if that's any harder. It really doesn't matter what the power is on the tangent. As long as there's an even power on a secant, you pull out a secant squared. So if I factor out a secant squared from here, I've got secant to the 4th left. But I pulled this out with the intent of that being the du, which means u has to be a tangent. I got to get these guys out of here. Secant to the 4th is secant squared squared. Secant squared is tangent squared plus 1. So I want to divert your eyes away from that one. We're leaving that one there. It's this one that we want to change. That's my du. Put it there in step 1. Let's get rid of secant squared now. Again, secant squared is tangent squared plus 1. I'll have to square it. But I did what I wanted to do. Pulled out a secant squared, I got everything else in terms of tangents. May as well do the Udu substitution now, and then we'll do the algebra later. So let's take u just to be tangent, du is secant squared, and we've got a polynomial integral. Gives us an integral that looks like u cubed, u squared plus 1 squared du. U cubed, u squared plus 1 squared du. It's a big old product. We got to do all the squaring and multiplying it out, and then we can integrate term by term. So first the squaring. U squared plus 1 squared is u to the 4th plus 2u squared plus 1. Now send the u cubed through there. Add powers when you multiply like bases. So we have a u to the 7th plus 2u to the 5th plus u to the 3rd du. Now integrate. We get u to the 8 over 8 plus 2 u to the 6 over 6 plus u to the 4 over 4, where each u is the tangent of x. So we can rewrite that as the tangent to the 8th power of x over 8. 2 6 is the same as 1/3. That'll be the tangent to the 6th power of x plus tangent to the 4th power over 4. Slap on the plus c to let everybody know you're done. That's an easy case. Power on secant is even, pull out a secant squared, write everything else in terms of tangents. If the power on secant is odd, pull out a secant tangent and see what happens. So let's give a few a try. So let's do the same example, but let's put a 5 right here. The same example, tangent cube would make it secant to the 5th. In order for this to yield us a nice, pretty UDU integral, we need both powers to be odd. Because then we pull out a secant and a tangent, that's going to leave you the tangent with even powers. We're going to want to get rid of the even powers of tangent with our Pythagorean identity. So both being odd is good news. Pull out a secant tangent. That's going to leave me a tangent squared and a secant to the 4. And we're saving this here as our du. When you underline it, that tells you I need everything else to the left of that to be entirely in terms of secant. So to get this in terms of secant, we substitute tangent squared with secant squared minus 1. Got our du term. Keep that underlined so that you know what your goal is. That's my du. So my u is a secant. So we're going to take u to be the secant of x, du, the secant x, tangent of x, dx. And so we have u squared minus 1 times u to the 4th times du. Multiply it out, you get an easy polynomial integral. We can integrate term by term. Multiply it out to get u to the 6th minus u to the 4th. Now integrate, we get u to the 7th over 7 minus u to the 5th over 5. U is a secant, so we get secant to the 7th of x over 7. Minus secant to the 5th of x over 5. We're done. Back on the plus c. Okay? So see how that's going to work every single time that's odd and that's odd. Not so great when that's odd and that's even. But it's doable. But when that's odd and that's even, we're going to have to do a little bit of integration of the parts. You're dying to see that right now, aren't you? If only it were just a little bit hotter in here. So, if the power on secant is odd, and power on tangent is even, you will likely need integration by parts. So let me see the tamest case I could do there. Let's just do tangent squared times secant to the first. Let's integrate tangent squared times secant to the first. I'm going to get those Pythagorean identities out here. I erased them over there. I need to look at them. Use one form of that, but I just don't know what. But look what happens if we try to use our odd power on secant strategy. We try to pull out a secant tangent as the du. That leaves me a tangent here, and then my secant tangent here. If that's du, this has to be in terms of secant. I don't have a secant there. I don't have a tangent squared there. I don't have an even power on tangent to use this. You say, well, why don't you just substitute in the square root of secant squared of x minus 1? Well, then I have to integrate the square root of u squared minus 1. Don't know how to do that either yet. Right? So that doesn't work. The next thing I'm going to try is trig identities. Maybe write these in terms of sines and cosines and cross my fingers, or just dive right on in here and put tangent squared is secant squared minus 1. I'm going to do that one. So this doesn't work. Nothing to substitute here. So I scratch that idea. So instead, what I'm going to do is replace tangent squared with secant squared minus 1. And when I distribute the secant of x, I get two integrals to do. I get this one and this one. I know the integral of the secant of x. Okay, so I'm going to go ahead and write that as two integrals. I'm going to go before the old partial credit route, do the one I know. I urge you to learn this one. The integral of secant to the first power is the natural log of secant plus the tangent. And that leaves me this integral to do. It's an odd power on secant, so we want to pull out a secant tangent. Can't pull out a secant tangent because there ain't no tangents. So this one I'm going to do to the side. This is going to be our integration by parts. I've got to write secant cubed as a product of two functions, one whose integral I know and one whose derivative I know. Well, I know the integral of secant squared, right? The integral of secant squared is tangent. So I'm going to factor that as secant squared times secant and try integration by parts on that. So let's go, hang on here. Let's just do this to the side. So let's try integration by parts. I said I know how to integrate secant squared, so I'm picking that to be the dv. That leaves secant to be the u. Integrate the dv, take the derivative of the u, and then plug things in. du is secant x tangent of x. V is a tangent. And we have uv minus the integral of v du. And so for our problem, uv is secant of x times the tangent of x. V times du is a secant times the tangent squared. Are you with me? Seen that before. I couldn't use my odd strategy. I've integrated a secant cubed. I'm going to integrate that thing. Let's get a secant cubed back out of it by replacing the tangent squared with secant squared minus 1. I'm going to distribute the secant through the parentheses there. I get a secant cubed minus the secant of x. I'm going to break this up into two integrals. So we have a secant of x, tangent of x, minus the integral of the secant cubed of x, plus the integral of the secant of x. So we've done this one. The integral of secant is a natural log of secant plus tangent. This is the one we started with. In fact, it's sitting over here. So not only is this integration by parts, it's integration by parts that becomes circular. So I'm going to pull this one to the other side and add it with this one. And I'm going to go ahead and integrate that one. So we get two of these. Then we have this, and the integral of the secant of x again is the natural log of the secant of x plus the tangent of x. So I can put that up here if I erase this muck. So I said add one of those to each side, gives me two secant cubes over there. I already we have this as the antiderivative, secant of x times the tangent of x. Then this one has a natural log of the secant of x plus the tangent of x. And so my integral of secant cubed is all of this divided by that too. And all of this goes right here. Okay? So when I put all of this right there, something didn't work for me. Oh, that's over 2. Okay, so then I'm good. So I'm putting all of that right here. I have 1/2 of the secant of x times the tangent of x. Let me just put it the way it is. That bit for my calculation over there, then minus that guy. Essentially, I'm done. There's some simplifying you can do. You could take the 1/2 of these, subtract those, and get minus 1/2 of those. Some manipulation of that is going to happen every time secant is odd and tangent is even. And I picked as my example the easiest case. If you're integrating something eventually down the line of secant to the 5th, but you should try it just for fun. But it has many steps to it. But in doing all of this, it's important to know what you know and you don't know. You had to realize that you knew how to integrate a secant, but you don't know how to integrate a secant cubed. You have to realize that you can't substitute this out. You got to remember what you know. And eventually you got to know as much as I know. Huh. I know. I'm a math goddess. If you weren't sitting, you'd probably be bowing or curtsying or something. But I wasn't always a math goddess. I was the kid at the back of the room going, what do you do? My calculus teacher was Dr. Gupton, and I had calculus every day at 8 o'clock in the morning. And Dr. Gupton was a little bitty skinny man, and he talked in a terrible monotone. And then we're going to substitute out the tangent squared for secant squared minus 1. Then you can see you've got a polynomial integral, and you just integrate. 8 o'clock in the morning. I'm like 18 years old and hungover as hell. It's a wonder I learned any calculus at all. Okay, the product of cosecants and cotangents works very similarly to tangents and secants. You got to remember that if u is equal to a cosecant, du is a cosecant cotangent, minus sign. If u is a cotangent, du is a cosecant squared with a minus sign. And then we have a version of the Pythagorean identity for cosecants and cotangents. So the strategy for cosecant to the m, cotangent, I should put the cotangent first because it takes the place of the tangent. Cotangent to the m, cosecant to the n. Use the same strategy as for secants and tangents. Where now the cosecant is doing the role of the secant and the cotangent is doing the role of the tangent. And the fact that if u is a cotangent, then du is a minus cosecant squared. So if you've got an even power here, pull out a cosecant squared. If u is a cosecant, then du is minus cosecant of x cotangent of x. So if you've got an odd power here, pull out a cosecant cotangent. Then the Pythagorean identity, let's derive the Pythagorean identity for secants and cosecants, or cotangents and cosecants. Starting with the big boy, sine squared plus cosine squared is 1. A cotangent is cosecant. A cotangent squared is a cosine squared over sine squared. So let's divide everything by sine squared. Then my identity says 1 plus cotangent squared. 1 over sine squared is the cosecant squared. So if I'm pulling out a cosecant squared, I want the rest of my integral to be in terms of cotangents. So I use cosecant squared is cotangent squared plus 1. If I'm pulling out a cosecant cotangent, I want everything else to be written in terms of cosecants. So I use cotangent squared is cosecant squared of x minus 1. If by chance this is an even power and that one's odd, this works to give you UDU. If this is odd and that one's odd, you're going to integrate by parts. Yes?
Would it be if m was even and n was odd, then we do by parts?
That's right. Is that not what I said?
I think you said they're both odd.
No, both odd's easy. Both odd is here. Cosecant even here. Cosecant odd, tangent even, cotangent even. That'll be the integration by parts. But you'll find out when you do them. So tell me how you would do this one. I'm just going to do one example here. I told you how to do this, but I told you real fast to see if you were really listening. I'm going to use my Dr. Jefferson monotone. Just like with the secants and tangents, it's the power on the secant that's important. So cosecants and cotangents, it's the power on the cosecant that's important. I got an odd on the cosecant. What should I do? Which one of those two works with the odd on the cosecant? First choice or the second choice? Second choice. This is if you have an odd cosecant. And this is if you have an even power on cosecant. So I'm going to pull out a cosecant cotangent. That's going to leave me a cotangent to the fourth. And I'm setting that up as the du. If that's the du, then the u has to be cosecants. I don't have cosecants just yet. I got a bunch of cotangents. But I can get rid of all my cotangents in terms of cosecants. Think of that cotangent to the fourth as cotangent squared squared. And each cotangent squared is a cosecant squared minus 1. And now it's the way I want it. You have a cosecant cotangent out there, you need everything else in terms of cosecants. So that you can be cosecant, and I got a polynomial integral. Can you see that? U is this cosecant. du is minus cosecant of x, cotangent of x, dx. And we have minus u squared minus 1 squared du. So blah, blah, blah. Okay? So that's all I want to say about integrals that involve trig functions. If you've got integrals that have different mutations, sines with tangents, cosines with cosecants, then try writing things in terms of sine and cosine and see what happens. So what you should do is try to integrate sine to a power by itself for n is equal to 1, 2, 3, 4, and 5. Do the same for cosine to a power. Tangent to a power. It's a little bit harder for secants. If you can do those for powers 1 through 5, I think you'll have a pretty good grip on what's going on. And I've done them, and I'll put them on Blackboard if you want to check. But I'd like you to try them yourself, and to quiz yourself. So you'll be doing 20 integrals. I said do 20 sit-ups, you could do it. So we do 20 integrals. Take a break. Take a little minute or two break. Take a 1 minute, 45-second break. Get some water, go to the restroom, scream. We come back and we're going to do some really fun stuff. You thought that was fun. All right, you guys at home, did I put anybody to sleep in there? You don't have to confess because I can't see you. I got a lot of stuff hidden from you. I wonder why I hid that from you. Let me turn my here. That's what you got hidden. Any questions while everybody's taking a break? All right, Reagan, good girl, baby. Probably should write bigger. I don't know how to get rid of the glare on the board. I tried shutting the lights off, haven't I? You guys ever played knockout in basketball? We can do the knockout calculus. I can put a problem up here, call somebody to work it. If you can't do it, you're out. Next guy gets a chance. Doesn't that sound like fun? What do you get when you win? The same thing you get when you win knockout. The respect and admiration of all of your peers.
And 100 for the class.
That'd be kind of fun. Put points on it, yeah. You get knocked out, you get like an F for the class, like that, you know, 100. You make it to round 2, you get a D.
So the winner should get like 5 points in the next exam or something.
5 points on the next exam. We can do it. Starting now, I'll write a problem up here and see who wants to be my first batch of knockouts. Because you have to do it up here, right? You can't just do it in your head or on paper. You have to do it with all the pressure of everybody watching you. Calculus knockout, just invented.
So what made you decide I want to do math for
the rest of your life.
Yeah. Well, I went to college initially thinking, well, I was first generation college, so I had no idea what college was. I thought an engineer drove a train, so I had no idea what engineering was. If I knew then what I know now, I think engineering would have been attractive. I was into athletics in high school, so I thought I'd want to be a coach. And I thought, no, I hate all my coaches. I don't want to be somebody everybody hates. So I thought, okay, computers are the next hot thing. This was way back when. But all the computer science classes were in the afternoon, and I had a job in the afternoon, so I had to change my major. I was pretty good at math, so I thought I owed society. I owed it to society to study math. And so that's what I did, just by default. The classes were in the morning. And back then, when you had to register, you had to go to the basketball arena, get in line, pick up a card for the class you wanted, punch card. That's computers are run by punch card. So I had to pick up a punch card for each class I wanted, and then take your stack of cards to the registrar, and they register you. Well, guess what subject had the shortest line? My major. So I didn't have to show up at 8 to register. I could show up and whatever, and there's my classes waiting for me. So that's another very well thought out reason to major in math. Classes were in the morning and the line was short to register. You want some career goals for you? There you go.
Did you go to Tech?
No, I did not. I was raised in Tennessee, and I went to a small college in my hometown called Austin Peay State University. And I only went there because if you graduate in the top 10% of your class, you got free tuition, as long as you keep the GPA. So I had to keep my drinking into control so that I can keep my GPA. So I just found that line. And drinking age was 18. I had 2 or 3 years of practice in high school. Yeah. We all back? Now comes the fun stuff. I made you go through all that boring stuff in order to do the fun stuff. We're going to try to do integrals that have some square root signs in the way, where the integral is not quite a UDU integral. It's not quite one of our inverse trig functions. It might be real close, but not quite. Yes?
Does that mean we can skip all that?
No, because when you do these fun integrals, they result in one of these. So this is going to be step 2.
Oh, no.
When you said fun, I thought you were talking about the calculus knockout.
Calculus knockout. But we can add this part to it so we can make it even more challenging calculus knockout. We can do the calculus knockout tomorrow if you've got nothing to do on your wellness day. You can just find an unlocked building and do calculus knockout. Okay. This is part 2, 7.3. Let me see where I gotta move that camera. Yep, can't see that. I gotta twist it back. That contain terms that look like either this one or this one, or this one. That's going to be one of the terms in your integral. It might be on top of a fraction, it might be on the bottom of a fraction, it might be all by itself, where u is some function of x. And you know we can't go inside the square root sign and just integrate the terms and square root sign and put the square root sign back on. No matter how hard you try to tell me you can do that, you can't. The square root sign's in the way. And we need a way to get rid of the square root sign. And our way is to make a trig substitution based upon the Pythagorean identity. Sine squared plus cosine squared is 1. So here are our Pythagorean identities. Let's see, if I divide by cosine squared, I get tangent squared x plus 1 is secant squared. Or if I have a secant squared of x minus 1 is tangent squared. The key to our happiness and success in doing integrals with those terms in it that aren't your ordinary UDU integrals is right there. If I have two things added together, then I want one of my things to be a tangent so that I can have something like this in there. If I've got a number subtracting a variable squared, then I'm going to take this and write it as cosine squared is 1 minus sine squared. So that's going to play the role of this guy. And if I have the variable squared minus a number squared, well, there, I'm going to let the variable squared be represented by a secant squared so that I could take a quantity like that and put a single term in it. We'll be able to get rid of the radical signs by replacing two terms with one. Replace two terms with one. And that one term will be a perfect square, so we can take the square root of it. So here my choice, I've got things added together, so I'm going to try to make it look like that. I need this to be a common factor, so we're going to pick u to be a times the tangent of another variable. So let's use a theta. If you have a u, then you need a du. Then du will be a times secant squared of theta d theta. That's for this case. And you'll see that that cleans up your integral and gives you a trig integral that you'll know how to do. This one has the variable squared behind the minus sign. So we're going to pick the variable to be some version of a sign. So here, we're going to pick u to be a times the sine of theta. So that when I square it, I get an a squared sine squared and have that common factor of a squared. Then du, derivative of sine is a cosine. So that pair will clean up your radical sign, give you a trig integral. The other choice is if you've got something squared in front of the number, then we're going to pick u to be the secant of x, or secant of theta. A times the secant of theta, so we have that common factor. Then you need a du. Root of a secant is secant tangent. So we're doing it u du substitutions. Do not forget the du part. Or x dx. At the beginning of my examples, I'll have x's instead of u's. But then I did it in the most general form so that if I have function of x back there, then you see the plan. If you use that as your plan, then life is good. If you invent your own plan, it probably won't work. All right, so look, here's an integral that it looks so innocent. Looks so innocent, but we don't know how to do it. Right? It'd be easy if I had x to the first power outside of the square root sign. Then it's a u du integral. But I don't have an x to the first power outside the integral sign. So it's not a u du integral as it sits. I can't just say that's the square root of 1 minus the square root of x squared. You can't distribute a square root through a sum. You can only take the square root of terms in a product. So we're going to try to make this look like a product. My variable is behind the minus sign, and the number in front is just a 1. So I'm going to pick my u to be, well, actually, I'm going to pick x, because I don't have a u. I'm going to take x to be 1 times sine of theta. Then the dx is cosine of theta d theta. Now let's substitute both those pieces in and see what happens. We get 1 minus the sine of theta all squared, which I'm going to write like this. Dx is the cosine of theta d theta. I still have 2 terms under the radical sign, but these 2 terms can be substituted out for 1. 1 minus sine squared is cosine squared. And bam, I can't take the derivative of the square root cosine squared. I'll get a cosine here. Radical sign is gone. Did I get an integral that I know how to integrate? Or did I get an integral that you know how to integrate? What's the integral of cosine squared?
Theta over 2 plus sine 2 theta over 4.
And we're done. No. My original problem had x's, so I've got to get my antiderivative back in terms of x. And so here's how I'm going to do it. Go back to my original substitution. X is equal to the sine of theta. So what's theta? Arc sine of x. So I know what to put here. I'm going to use a trig identity for the sine of 2 theta, and I'm going to write the sine of 2 theta as 2 times the sine of theta times the cosine of theta. So I'm going to use this trig identity right here. Two sine of theta cosine of theta is sine of 2 theta. Because I know what the sine of theta is. The sine of theta is x. And if I know the sine of angle theta, then I certainly know the cosine of angle theta with a little bit of work. Here's the little bit of work. I'm just going to draw a right triangle. Put angle theta down here. The sine represents the ratio of the opposite side to the hypotenuse. So think of this as being x over 1. And I'm going to label the opposite side x and the hypotenuse 1. And I want the cosine of that angle, so I'm going to need the adjacent side. So do the Pythagorean Theorem. Adjacent side squared plus x squared is equal to 1. So solve that for a. Subtract the x squared, take the square root, and this side is going to be 1 minus x squared. And so the cosine of that angle is adjacent over hypotenuse. And so now I get my final answer back in terms of x. Theta is the arc sine of x. And I got this 2 on the bottom. I'm going to cancel this 2 with this 4. Sine of theta is x. Cosine of theta is the square root of 1 minus x squared over 1. And then I've got this 2. Yes?
Do you not just leave the cosine of theta as cosine of sine?
Say it again?
So in the red, you have cosine theta, yeah?
Yes?
You not just substitute that theta for arc sine of x? You just leave it like that?
That'll work. That's kind of wimpy, right? I'm going to call it what it is. That's wimpy. If we had a definite integral, then you would have to know how to compute that composite function for various values. So if I were now evaluating this from 0 to a half, then you should be able to figure out those numbers more easily from here than you would from, say, the cosine of the arc sine of 1/2. Okay, so see the difference between and wimpy? Want to see that again? And wimpy? Almost burst out of my sweaters making those biceps. But it's okay if you do that. Just know that in my mind, I'm calling you a wimp. Is that bullying? Is that allowed? Because it's in my mind. I didn't really say it out loud, wimp. Calculus sissy. I'm going to go that far. Okay, so wasn't that cool? Do I need to do that for this integral? It's essentially the same. Do I need to go through all those steps? No, this is a known integral. Just because it has a square root sign in it doesn't mean I have to do all those gyrations. I already know this integral. What is it? Arc sine of x. So if you did all these steps, guess what you'd get? You would get the arc sine of x, but with a lot more steps. Like this has almost no steps. But if you did all those steps, you'd get this with a bunch of steps. So it helps to know what you know and know what you don't know. Okay? All right, so let's try some of the other ones. Do I need to do all of this for this integral? Is it a no or a new technique? Is that almost an answer? Do you know how to do this without doing all that crapola? It's a U-sub. Degree on bottom is higher than the degree on top. Take U to be the stuff down here, and there's your du. So that's already a UDU integral. Now, if I did this, then I'd probably do that stuff. Okay? But I know how to do it without the x squared. I know how to do it with the next to the first power. Once I have something different, then I can't do it. Okay? All right. Know what you know. Do you know this integral?
Yes.
That's an arctangent, right? That's a UDU, right? That's, I don't know. Once I put that square root sign on there, it's not an arctangent anymore. Once I took the x off the top, it's not a UDU. Okay, so don't just jump to this. This should be one of your last resorts because you've seen how long that little short innocent problem was. Look for UDU and known integrals first. And then if you're still tasked with getting rid of a square root sign, there's our trick. I've got things added together, so the suggestion is to take the variable and replace it with something times a tangent. What number am I going to use in front of the tangent? 3. Take x to be 3 tangent of theta. And then let's watch the magic. And again, if you pick an x, you need a dx. So don't forget the dx term. Rid of tangent is a secant squared. Now, if we put that in correctly, we should be able to, in a step or two, get rid of the square root sign. So I'm putting in an x squared. So I'm squaring both of these. Now I'm putting in a dx, and I'm going to put it in on top as a 3 secant squared theta d theta. So here's my dx term. So picking that number in front of here means that after I square it, I have a common factor. I always need that. So let's now, inside the radical sign, factor the 9. And then I'll have a 1 plus tangent squared as the other factor. And I just erased it. 1 plus tangent squared is a trig function. Which trig function is 1 plus tangent squared? Secant squared. So I made this sum into now a product. And they're a product of 2 perfect squares. I can take the square root of each term in the product. And now my denominator is just 3 secant of theta. So the 3's cancel, one of the secants cancel, and now we just have to integrate secant to the first power. Do you remember that one?
Natural log of secant theta.
Yeah. Natural log of the secant of theta plus the tangent of theta. And now we just do more. Don't stop here. Let's go back and figure out what these two are in terms of our variable x. So that comes from the first substitution. X is 3 tan theta, so x over 3 is going to be the tangent of theta. So a quick picture will tell me what the secant of theta is. For the theta here, there's my right angle. Tangent is opposite over adjacent. Pythagorean theorem says this squared plus that squared is this one squared. So that'll be the square root of 9 plus x squared. If you do this right, the other term in the triangle is always that term in the integral. Okay? But now the picture tells me what the secant of theta is. It's hypotenuse over adjacent. So I take that over that and put that in for the secant. Tangent of theta is x over 3. And so we have the natural log of the square root of 9 plus x squared over 3 plus the tangent. Oops, no tangents. Get out of here. Tangent is x over 3. And now we're done. But using properties of logarithms, I can also rewrite this answer like this. Where the heck did the 3 on the bottom go? Those two are equivalent. This has a common denominator, so all of this is over 3. I've got the log of a fraction, which is the log of the top, minus the log of the bottom. So minus the natural log of 3. The natural log of 3 is just a constant, so it got sucked up by that constant. Okay, so sometimes you'll see the answer written like this. You can leave it here, it's perfectly fine, but I didn't want you to be perplexed if you saw that. Okay? So if you see a plus sign here, that's our plan. We're going to replace the variable with the square root of this number times the tangent of theta. Yes, sir.
I thought you said that what we did before was going to be the second part of all that.
Yeah, we had to integrate secant. So as before. I'm, of course, doing the easy examples. All the hard ones I'm saving for you. Why would I want to do the hard examples? I just spent an hour and a half doing hard examples. All right, we're going to need to try one of these. Do we have time? Not really. Not really. Unless I talk professor, then we have time. Well, maybe we'll just talk it through. If I had the x here, that's a known integral. Agree? That's an inverse secant. If I had the x here, that's a UDU integral. Agree? If I have no x or too high of a power of x, maybe an x squared and an x squared, then it's not a known integral. Then it's the third case. And we're going to replace x with a times the secant of theta. And then hopefully the magic happens and we get rid of the square root sign and get a trig integral that we can do. Okay? All right, I'm going to leave you at that. Let you take tomorrow off, unless you want to show up here and we'll do knockout calculus. I bet I'm the only one who shows up, though. How embarrassing would that be? Have a good day off. Look on Blackboard. If you're missing any assignments that you haven't submitted yet, the write-ups, do it. I'll take things late. Let's fill in the little empty boxes with scores. If you turn something in and it's not there yet, just remind me that I still need to grade it. Have a good, long weekend. Well, tell me when, and I'll make sure I'm here.
Okay, you want me to send it?
Yeah, that'd be good. That'd be good. Thank you, thank you, thank you. Thank you.